Yeah, just to give you some context on what I do, I'm CEO of a company called Active Group. We do software project development in many different functional languages. In particular, this talk will draw from our experience doing professional training for professional Java programmers or whatever who want to learn about functional programming. We also run a German language blog on functional programming. More importantly, we run a very nice conference for developers in Berlin just about a month from now, which is almost even better than this one. And there's still some tickets for that. For this talk, what's relevant is that I have been teaching programming for a very, very long time. So I taught my first official course in 1987 at an American high school. Who was alive at that time? So, oh, okay, well, it's about half. There we go. Anyway, so I've taught programming to many different people, in particular to computer science majors, computer science minors, humanities majors, high school students, my kids, to their detriment probably, co-workers and friends. So everybody suffers around me. But maybe not everybody. So I'm sure if you teach programming, right, you've made this experience that if your student base is sufficiently broad, that students will come up to you and say how great that stuff was that you taught them, right? Functional, whatever. If it's functional programming, you like functional programming, so you're going to teach your students functional programming. So that's the most wonderful thing ever. Somehow these students, they often look like this, right? I don't know if you've noticed. And this fact that you will always have students who are very excited about what you're teaching them can often mask that there are problems with some of the other students that you're teaching them. So I had this epiphany, I think, at the end of the 90s when I was teaching at the university level, when we did a broader examination of how students were actually doing in our class, that indeed we had a bunch of students very happy about what we were teaching, but a lot of the students, well, they were doing okay, but they were not doing as well as we hoped. So they kind of, from our perspective, they were really being left behind and we never noticed. And why you don't notice in a course, that's a separate talk, I guess. But students don't tend to come up to you and say, "Oh, I have trouble following your material." At least not in Germany. They tend to copy somebody else's homework. They tend to just not follow the course and then have problems at the final exams. So there's many different mechanisms which might prevent you as also an authority figure from learning about the failures of your teaching. And so I think, looking back on my career, probably most of the teaching I've done, I would probably now consider a failure. So of course, we're doing functional programming. We know functional programming is great, right? And so it's easy to come to the conclusion that functional programming, because it's great, it must also be great for beginners. And I think the beginning of that thought was a book which first came out in the mid-'80s, which you might have seen, sometimes called the Wizard book or the Purple book, called Structure and Interpretation of Computer Programs, which was, I think, the first sort of broadly applicable book coming out of MIT about their introductory teaching. And it used a functional language, and it focused on functional programming. And the functional language that it focused on was Scheme. And so if you who's read that book? Who's looked at it? So most people here. So it's one of the great books of computer science, right? And it reads extremely well. And I remember when I first read it, I put two things together, right? I love this book, and this book was written for the introductory course, and therefore it must be a wonderful book for the introductory course. And of course, it uses that really nice programming language, which is really simple and it has this nice syntax and it's functional. It's easy to transition to another functional language. And so it must be this wonderful language for beginners. Unfortunately, these are all the wrong questions here, right? If it's a great language, is not the relevant question that you need to ask when you're teaching beginners. And so I think over the years, more and more people realize that even though this Purple book is a wonderful book, it's a terrible book for the introductory course. It just does not work. And I think for the longest time, a lot of people believed that the problem was just that their students weren't as smart as the MIT students, but if you talk to the TAs from MIT, they would tell you that it never worked at MIT either. And in fact, MIT has also abandoned this approach in the meantime. And again, there's many factors responsible for that. I mean, one of them is, of course, that your students are not like you or like her, if you know who that is. If you don't know who that is, you might know who that is. But I encourage you to find out who that is. So really, when you talk about teaching, a lot of people think it's really important that you're passionate and excited and that you love what you're doing. You might love Erlang. I would encourage you not to do that. I would encourage you not to think about what you're excited about, but think about what works and what is important to you in the course. So in particular, what is important to me when I teach is to teach what I call a systematic approach, something that students can follow when they construct their own programs to solve problems. I'm sure we've all seen, and again, that's in a whole different talk, we've seen a lot of terrible code that maybe our past selves wrote or our students wrote, and I would really like programming to be more systematic, and I think that's one of the promises of functional programming. Maybe it's not one of the promises of programming with fancy type systems these days, but generally with functional programming, you can be very systematic. In particular, I think I made that decision at the end of the 90s that I would try not to be too excited about students coming up to me and saying how much they love my course, but instead I would be more interested in results in the final exams. And we found out that there's just a lot of factors which might keep a student from effectively learning your material. Those don't necessarily have anything to do with functional programming. I mean, you need to somehow create an environment where there's a lot of practice that students are getting. Modern IDEs are often very much too complicated for beginning students to use. Emacs is great. It's not such a great IDE for beginners. The programming language itself, even though you might think it's wonderful, might not be so wonderful for beginners. And there's the whole question of didactics, and maybe the question of didactics should inform all the other factors in that. In particular, one aspect with didactics is if you look at if you take any random book on programming out of your shelf, chances are that it will use an approach that I call teaching by example. So it will introduce a couple of constructs from a programming language. It will use them. It will show a couple of examples using those constructs. And then it essentially tells you to go forth and create your own programs using the constructs that you've just seen and somehow gather the knowledge about how to construct programs from the examples that you've seen. And again, that works with the Sheldons. They will learn anything that you throw at them. You can, whatever, do Turing machines or something. But my very consistent experience has been that it doesn't work with sort of the broad student population at large. And the results are, first of all, that you get students who are frustrated. You don't usually see them being frustrated, but they are frustrated at home. And they're just not able to construct programs successfully. And if they are successful at constructing programs successfully, those programs often look like that. So, and I don't know what your experience has been, but it's been my very consistent experience. So I want to encourage you to think about different set of points of reference. So a very systematic approach to teaching how to program was pioneered by Matthias Fellheisen's group, the PLT group, also in the late 90s. We did our own German language book to correspond to that book, and we have an ongoing project called DeinProgramm, unfortunately German language, on doing a German language curriculum that is successful at teaching how to program. Strangely enough, there's a lot of phenomena I can't really explain about successful and unsuccessful teaching. I'm not really a didactics professional, but one of the things that we've discovered is in professional training is that this approach works across a wide variety of different settings. So it works for high school students, it works for university students, it works for professional programmers, it works for students who have no prior exposure to programming, but it also works for people who've done Java. And it's based on a very systematic approach to teaching that is called the design recipes. And maybe you've heard that word before. One thing I want to impress upon you is that it's kind of difficult to learn about the practice of design recipes from reading. And so I want to do that in that talk today. First of all, the design recipes, so again, they try to be a very systematic approach to programming. In particular, usually what happens in the beginning is when you solve a problem with a program, you write a function. And when you write a function, you always go through a sequence of steps in that particular curriculum. And so you do, we'll see what that is in detail. You don't need to remember any of that. And Matthias' sequence is slightly different, but the important thing is that you always go through that sequence and you make your students go through that sequence every single time you write a function. And now we're getting into territory that is very far away from doing fun things in your class. In fact, if you look at this, and you're going to see me, you're going to think this is, Matthias Felleisen is a German. I'm also a German. We're into bureaucracy, right? This is an extremely bureaucratic approach to programming, and it might not seem very motivating or exciting. I mean, in particular, if you read Matthias's book, it is just not as exciting, as endearing as the Purple Book, right? It's a great book, but it's much more successful at intro teaching, but it's not, endearing. It's not anyway. So I'm just going to try to show you a classic example of functional programming. I think that Matthew Flatt came up while PLT was still based in Texas. This is about animals on the highway in Texas. And there's two different kinds of animals there. There are armadillos and there are rattlesnakes for some reason. Okay, so the way this works is, you might remember from that list or not, there was a very important step called data analysis. In fact, this approach is very much data-centric, or you Haskell programmers would think of it as type-centric. So the first thing that you do is you try to put together a natural language description of your data. In this case, you might say an armadillo, for purposes that you'll see, has the following properties. It's either alive or dead. It might have been run over by a car, which is what happens on the Texas highway. And it has a certain weight. And so I'll greatly compress how this approach works. In fact, there's lots of intermediate steps which I'm going to skip or gloss over. The important thing is that you sort of try to bring your natural language description of your data into a form like this. And in this case, you look for the words has the following properties, and then there's a list of several properties after that. And this is, the design recipes then teach you. When you see that, it has these following properties, or it consists of these parts, or something similar, is that you're looking at a phenomenon called compound data, or you might say it's an aggregate or something like that. But in this approach, it's just called compound data. So I'm going to try to take off there, and is anything happening there? Yeah. So this is going to be fun and exciting now. So I don't know how I'm going to do this. So anyway, well, I kind of glossed over the fact, for example, that this approach comes with its own programming environment, right? This programming environment is called Dr. Racket, and it was made specifically for beginners. And when you start it up, it will start up like this. It has a mostly empty screen. In the upper half, you can write a program, and you will see very few buttons up at the top. So we had to make a few adjustments at the last minute about how that works. So you remember it said an armadillo has the following properties. Did I actually write that? Yeah. Is that big enough? People at the back? No, it's not. Oh, this is going to be so much fun now. Yeah. Better? Okay. So anyway, we said it has the following properties. It says it's alive or dead, and it has a certain weight. So I said we're looking at compound data, and then you can actually write almost like a recipe. Well, it's called a design recipe. It's almost like a cooking recipe. So when you see that, you write what's called a record definition. And so again, these languages at the first sight, if you're not very familiar with Scheme, they might look like Scheme, but actually this language has seen many changes from the Scheme that it started from. So what we teach is that when you see compound data, you do a record type definition. And the way that looks is you say, well, there's an armadillo. I'm just going to shorten that to dillo here. And an armadillo is constructed by a function called makeDillo. Again, I'm skipping over a lot of intermediate steps. There's a predicate called dillo, which we'll see later what that's good for. And then it has, well, the data definition that you saw, the comment at the top says, and I can't tell you how important that is, it has how many parts? It has 2 parts. So you might think this is the most trivial thing in the world. So we try to impress on our students. You count the parts, and you make sure that they match up the fields in the records. And you would be surprised if you're not very strict about that, how often that goes wrong. So we said, well, there is Dillo alive, which is the name of the accessor, and we'll get into that in a minute. And it has, you might think, type Boolean almost, and you'd be almost right, but not quite. And we'll just make the weight a natural number. So now we have, so as you saw, right, from the data analysis, the second part followed almost mechanically from the first. You've got to think up a few you've got to think up a few names, but that's about it. What we then ask students to do at this point is, well, for example, for the records, you have a record constructor function. How does this whole thing with the records work? It was, well, you can write what we call a signature. It looks like this. So we say, well, make Dillo, it's a function, in goes a value for each single field of that record. And so, and out comes a Dillo object, right? And I think the way this is going, I'm going to really have to shorten this a little bit. And with that in hand, we can write examples, and that would be the next step, right? Is we write examples for the data for the data definition and for the code that came out of that. So we might construct an armadillo that says, oh, it's alive and it weighs 10 kilograms. And we encourage students, in fact, we asked them, to always create a connection between the data and the information that it represents. So in this case, it represents, well, an armadillo, it's alive and maybe it weighs 10 kilogram, right? And we'll do a second armadillo and maybe it's dead, it's been run over. And it weighs 12 kilograms, right? So, so there you go. Now we have examples for that data. We can always try that out by pushing that green button. I'm not going to do that because it's kind of difficult with the mouse cursor here, but I can push a button. And down here we can look at, here's a REPL. I'm sure you're familiar with that, where you can look at the data that you've created. Maybe for the Haskell programmers in the audience, so this thing up here, it looks like a type signature, right? But it isn't. In fact, if you put something else here, 12 or something, it will say, well, there's a signature violation. And that's because, well, of course, there was a violation of something there. It says Boolean, and we put in a number. So in particular, so we got a 12 here, and there's a signature here. In fact, we violated two signatures, the one up here and this one, right? And you might have wondered at the time, is the signature there was redundant with the record definition. But my students actually asked me to write that down at some point to really make it clear. So we can leave that out after a while, but it's a bureaucratic approach, so we write a lot of things down. How are we going to do this? So now we might ask somebody to write a program that does something with that. Has it become clear why it's not a type error? You could write it. It will tell you the actual value that violated the signature. So it will run your program and check it at runtime. Questions so far? We're doing? Okay. So we might write a function that says, well, feed an armadillo. And so the first step of the design recipe is you write that short description. Just write one line. So that's that. That's the first step. The second step is you write a signature. Signature forces you to think a little bit about the name that you're going to give that thing. And again, you can imagine that I'm glossing over a lot of detail here. So in this case, when we have a function that deals with state, well, an armadillo object or an armadillo state object goes in, and an armadillo state object goes out. And the next step would be, well, now we've written a signature. Now what we could do is we could write a few examples and turn those examples into test cases. So testing is integrated in those teaching languages. So we could say, well, if we're going to feed Dillo, well, good thing we created some examples. So if we feed that armadillo D1, then we would expect an armadillo that is still alive and that maybe is slightly heavier. And if we feed that second one, well, that's dead, so that can't eat. Well, I'll just keep it simple. Let's see that comes out. So now we've written test cases, and as you can see, is we wrote things in the order so things occur in the program in the order that we wrote them, right? So then the next thing that we do is, well, we can write a function definition. We already know what the function is called, and you might think, well, this is a trivial thing, right? Is you teach people, you just put down the same name that you put up there. It makes sure all of these bureaucratic steps ensure that students make progress. And if you've taught for any amount of time, you know that one of the problems that you have to fight is that students stare at an empty screen and they don't know the next thing that you're supposed to do. And that's what this bureaucratic approach, that's the problem that bureaucratic approach solves. So in fact, we know a little bit more because the signature says, well, a Dillo object goes in, Dillo object comes out. So we know we're going to need to write a Lambda expression with one parameter. And again, we teach very strictly, these things have to match up. If your signature has one thing going in, there needs to be one parameter here. We can do more because, and you know, I put down 3 dots there. The 3 dots, we actually make our students put down those 3 dots, and I write those 3 dots in class, right? So I'm not going to be able to convey the full amount of bureaucracy involved in this, but that is one aspect of that. And in fact, the programming language has support for those 3 dots. Well, not very much, but a little bit. So the next thing is we know a Dillo goes in, right? A Dillo is compound data. Usually if we want to do something reasonable with compound data, we need to look at the parts. So without even thinking about what that function does, just looking at the signature, we can now put in a couple of programming elements, again, that keep students, that enable students to keep making progress. So we know we should be looking at the parts. In this case, this means we should extract from the armadillo if it is alive and how much weight it has. And these are just sort of building blocks for the function that you're building. We know more, though. We know that the function produces an armadillo as its output, right? And that means that we need to construct that output because that's also compound data. So we need to call that, call the constructor from that. So, and usually when you get to that point, so this is stuff that we can put down even without knowing the problem at hand, just looking at the signature. And very often students are then successfully able to figure out what goes on. We can do even more here in this case because our data analysis would teach us that there's 2 different kinds of armadillos that are different with regards to this problem, namely live dillos and dead dillos, right? And that teaches students to put in a conditional. So in this case, there would have to be an if that dispatches on this. This would mean, so there's explicit, I'm sure you're noticing, I mean, there's really explicit written down instructions that go along with this stuff. So, and we have this maybe. So now we know if the armadillo is alive, well, we need to sort of fill out that form and see, well, after feeding, is it still alive? Yeah, it's still alive. And moreover, the weight after, we need to fill in the weight here, and the weight after is just this added to that. So usually when students get to that point, they're able to fill out that form. So in the other case, we would say, well, Dillo is still dead and it has the same weight as before, and then we get rid of the ellipses. Okay. Strangely enough, that helps our German language students. It says that the operator must not be a number. And so we need to put in a space. And Oh, we haven't done that yet. Oh, and that's when, we get, well, unfortunately, German language error messages. In particular, this one says the test result for the if is not a Boolean. So instead, it's the number 12. And we can then look at the test failure and see where that happened. So that's where that happened. So good point. Thank you. And huh? Oh, it's supposed to be alive, right? Yeah. So anyway, so that. There's a number of. Yeah, looking at the clock. Yeah. So we can do a little bit more. So maybe I can push that button. So there's a bunch of other tools that come with this that help beginners. So for example, there's something called the stepper, which shows a program evaluation in a very nice way. So you can really see that this programming environment is something that's tailored for beginners. I hope that's visible. And I think before I spend too much time sort of hurting my neck, I think you sort of got the basic point here. So does that work? So, as we go on, we might go and say, usually, if this was going a little faster, I would then add rattlesnakes. You saw that on the picture, and then we have both armadillos and we have rattlesnakes, and then we might say, well, really, we want to be able to feed any kind of animal, so we want to mix the snakes and the rattlesnakes and the armadillos together, so you get to a concept that we call mixed data. And you might call it a sum type or a discriminated union or something. That doesn't really matter. We just happen to call it mixed data. And again, what you do is you do a data analysis. Data analysis will yield something like an animal is one of the following. It is either an armadillo or it is a snake. From that follows a piece of code. And again, all the instructions for creating the intermediate products are basically very explicit about what to do. So, I see your eyes glazing over because this approach is so boring when you look at it as a teacher, right? It is super, super bureaucratic and boring. And funny thing that quite often happened to me in classes, I would get bored myself, right? And I would leave out intermediate steps, but then my students would come and say, no, no, no. You taught us to be super bureaucratic about this, so you have to be super bureaucratic about it yourself. And so, it would look like this. But this effect would pass after a few weeks because what it really does is it enables students to be able to successfully write programs. And that is the most motivating and exciting and endearing thing that you can do in a class. So this picture pretty much changes into that picture after a while. And we found this to be fairly robust, not just, so in Tübingen, for example, this has been in place for many years now, and a number of lecturers have done that, and it's very robust across lecturers. We still find ways to improve. So, in particular, you might have noticed, well, those languages, they started out from Scheme, which is why you see the funny syntax with the parentheses, which you might dislike, especially if you're a Haskell programmer, but the students, they dig it. And you just, and that's what Matthias did, and we did the same thing too, is you observe how your students are doing with that programming language, and then you pretty soon you discover that you need to make changes. And the great thing about the Racket system is that it makes it really, really easy to make changes because it's a toolbox for creating languages. And so when we started out modifying the languages, we would just ship a new language every week in class. Things have settled down more since then. But we're still making changes. In fact, the next version of Dr. Racket for our teaching languages is going to have significant improvements. But this is, you don't need to, if you're not starting out, if you want to do this, right, if you're not starting out with Scheme, you can do the same thing. So recently at ICFP, Chris Smith talked about his efforts to make Haskell into a good teaching language. And he found out that also he has to make many, many, many changes. Many small changes, but many changes to make it more palatable as a teaching language. And there was the earlier Helium effort There's other efforts for Java to make special programming environments. So that's also one of the messages. Of course, as a professional programmer, you love your Emacs or Visual Studio Code or whatever it is, whatever the tools of your trade are, but they're not necessarily the best tools for teaching. So in particular, Program by Design, the project around Dr. Rackett and this book, How to Design Programs, it includes these design recipes, which is a strong didactic foundation for teaching programming, but also it comes with programming language, or actually there's a sequence of levels in these programming language designed for learners, and also programming environment designed for learners, not for teachers or professional programmers. So, well, I think Matthias has been at it since the mid-90s, so many, many years of experience have gone into this, and it's required many years of iterative refinement to get to that point. So if you want to teach somebody how to program, I think there are a couple of significant questions that you need to ask yourself. Where do you want to get, why teach a specific language? Is it because of your personal preference or because of your experience that it's actually a good language for teaching? In my experience, none of these languages is a good language for teaching. Instead, we use specialized languages. And I was surprised to find out that this is true even for professional programmers who are used to seeing crappy error messages and Baroque syntax and whatnot. We tried that out in professional training. We found out that using the teaching languages is better. Even when somebody orders like a 3-day Haskell training, we do this for the first 2 days, and we do Haskell on the last day. And it works quite well. You might have noticed I didn't really say anything specific about functional programming here, and we don't usually talk to our students about that. But of course, that's what we're doing. And so the good news is functional programming is eminently suitable for teaching, much more so than object-oriented programming. Maybe another question that leads somewhat outside this talk is in today's society, it's seen as a given that everybody needs to learn how to program, right? For whatever reason, right? Because the technology sector needs more warm bodies or something like that. We're seeing lots of IoT devices coming out in the distant future, right? A lot of them are vulnerable in many ways and are crappy in many ways, right? Do we really need more devices in the future like the ones that we've had in the past? And maybe we need to adjust our position on who needs to do these things and how does it need to be done and how does your teaching need to reflect that. And with that, I'll leave you. Thank you very much.
Okay, thank you. And there are many questions. Okay.
That was a nice talk. I was just wondering, for how long have you been applying this principle based on the book?
I think for 18 years now. Yeah, so we started in the late 90s, and first version I think came out in 2000 or 2001.
I have a couple of questions.
Yeah.
So one was that you were saying that you started kind of appreciating positive feedback from a subset of your students, but what you actually care about is test results. How did this methodology affect test results, and how do you incorporate test results into iteration? Like, what's the process of deciding bureaucracy is what matters?
Yeah, very good questions. So if you look on our websites, you'll see that we've actually done some publications on this. What we would do is we would look very closely and at a great level of detail at our final exams, also at homework problems throughout the class, but mainly at the final exams. And that's very coarse-grained, but it's better than what a lot of people do. So we would try different approaches. So I can tell you, there was one particular chapter in the book, not accidentally, on imperative programming, where we just completely failed. And we tried to improve the chapter every time, and we were very thorough about it, and it just wouldn't get better. And so we figured that's great news, because that means we can just ditch 2 weeks of the class and do something else there, right? And so you get into that different mindset after a while. And we're just going to do a little bit of hand-waving about how imperative programming works, a few squiggles on the board and so on. Now, depending on how you look at it, is test results got significantly better, right? So, so all the care, I mean, that's really a problem, is all the care in the world with creating your teaching material might not go in the right direction. And so that's why it's very important to incorporate feedback, any feedback that you can get, and any feedback outside from how much they like it. Yeah.
So you spoke a lot of methodology,
Yeah.
I think mainly, and so when I started programming, I realized that what really kept me into it was that the target problem for me was interesting. I wanted the result always, and I felt like a magician basically when I was learning. So when people ask me about learning programming, I always tell them, well, I think the main thing is you need a thing that you want the result of. What's your opinion on this? Is it important, do you think, or?
I think it's important to a point, right? But the problem is this approach to teaching has also created a lot of problems. In particular, I don't know how it is in your country, but in Germany, right? Every year there's an educational project that says, oh, we're going to make very important, we're going to make very interesting problems or motivating problems for students by doing robots, right? I don't know, are you familiar with that? Right, right, and so great amounts of money and effort are being poured into that, and unfortunately, the value from the programming examples you need for robots that you can do with students don't have much value in terms of programming skill. So I think those two things need to go hand in hand. I mean, what we do is what has been quite successful is from the very beginning. I haven't showed you this, but Dr. Rackett and the introductory languages, they have an algebra of pictures, and that extends into creating animations in a purely functional way, and that lets you write video games. And so that's usually what we did at the university level. About halfway through the semester, people are able to write a substantial 80s style, Frogger or something video game. But I found that aspect not as important as making sure that even though your example might be boring, is to ensure that your students are successful at solving those problems on their own, right? And I've seen students who are going, oh yeah, I've calculated, how much my electricity costs, this, and they get a little bit excited about it, right? Not very excited, but a little bit excited about it. It's a super boring problem, but they were able to successfully solve it on their own. And that's what I think, so you need to put that in front and not how exciting or motivating your example is. Make sense?
So how is the transition process from your teaching language to a non-teaching language?
Well, it depends on the target language, of course. I mean, this you might have seen, well, no, you didn't really see it, but these teaching languages are designed in such a way that the concepts that we teach them map one-to-one to programming constructs, right? And it really depends, in particular when it comes to data modeling. So these concepts exist in almost any programming language, certainly in any functional language. So what we just go is we say, oh, compound data, how is that done in the language that we're looking at now? Mixed data, how is that done in the language that you're looking at? The answers vary, right? If you're doing Haskell, you say, well, compound data, it also has records, but it also has algebraic data types. If you want to do mixed data, you need to create an additional data type, and all of that stuff you can then cover very, very quickly. And so you just explain how the concepts that they now know about, how they map to that programming language, and then you can go do whatever you want, because people know. But by that point, people can do a lot of fancy stuff already. That goes quite quickly. So we typically get to monads in that single day of Haskell for people who've only programmed Java before.
You said that the best languages for teaching programming are the dedicated, specialized languages made for teaching.
Yeah.
But if you were to teach somebody who is a novice in the programming world, and you would have to choose from among the mature production-ready languages, like real-world ones, not teaching languages, which one would you choose?
I think they all. Yeah, I really can't tell. I can't tell you. I don't know. They're all not very good at this, right? Whatever they have at hand, I guess, is about. I mean, it really. Matthias talks about this in more and more length. It's just that there's, if you could get into this, there's just so many problems. I can tell you which language I would not choose, however, right? I have no idea how to do systematic development using Python. So stay away from that at all cost, right? So does that help? Yeah.
Thank you.
Okay. Do we have other questions? Yeah, we have 1 minute.
You mentioned you've taught your children programming. So what's your opinion? Does it make sense to teach programming to 8-year-olds? Would they be better? And what kind of, do you use visual languages or you use Dr. Racket? Or?
No, I use this.
So using some kind of language where you have a robot and you,
Sorry?
Yeah, where you just have instructions for a robot to.
No, I don't.
No,
No, I don't.
So,
so they program. I mean, my kids, they mostly program to create pictures, right? With that picture algebra I told you about, and that. But I mean, that's not a. I mean, again, you know, your children, they're probably not a good model for this, but for that you want to apply to everybody else. But it does work for. So my 7-year-old daughter just started doing this. In particular, maybe that's where your question is aiming a little bit. There are programming languages aimed at little kids, right? So I think this works well in a broader sense from about the age of 11 on. So I wouldn't recommend to do it in a class of 9-year-olds or something like that. It just happened to be that my kids got indoctrinated naturally at the dinner table. So that's one of the questions, right? I don't really have a good answer whether children should really need to learn programming before that age. The problem with programming environments that are designed for that, like Scratch, is really that there's no good path then to do, you know, systematic, more serious programming later on. And so I don't see the value of doing that. So my experience, or well, my conclusion under the observations that I've made over the years is that if you're going to teach programming, do it right from the beginning, and don't just go, we're going to just futz around a little bit, and then later we'll do the real thing.
Okay, thank you for a nice discussion. Yeah, I think it was a really good research track this time, and probably we will need to ask organizers for more time and more space and more everything. Okay, so we should thank our speaker again. Thank you.